All right, scientific method. So different parts of the method include observations, hypothesis, doing experiments, and then finally proposing a theory. Now, if that theory doesn't work out, you got to do it all over again. So the point of a scientific method is so that way you can find ways to answer questions because of an observation that you make. So let's say you were at school and you saw a flock of birds flying over the pond. Well, by the time they got to the middle portion of the pond, they all fell out of the sky and just were dead for no apparent reason. So you're sitting there thinking, what in the world just happened? You're sitting there watching another flock of birds come by, and they did the same exact thing. Now you got to start asking questions. What is going on here? Am I living in the Twilight world or the Twilight Zone, or what's going on? So, being a scientist, you come up with and you say, okay, well, maybe the flock of birds are dying because they're hitting a wall. It's very possible there could be an invisible wall there. You don't know. So what do? You get on a boat, you go out towards the middle of the pond, and you go probing for a wall. But you don't find a wall. So therefore, that hypothesis is now gone. So another hypothesis would be, well, maybe there's some gas being released from the pond that the birds intake, and that's what's causing them to die. Well, now you got to be really careful because if there's a gas that could affect them, it could affect you. So now you got to figure out a way to go capture that gas and then do the experiments to figure out what kind of gas it is. So these are all just different things that happen. So it's just a simple question that you ask yourself from an observation, and then you move forward with answering those questions. So now, just a couple little details about each of those parts. So observation is just something that you observe in nature. Hypothesis explains the observation. The experiments is what's going to help prove your hypothesis, and then finally, a theory is what you design around that hypothesis and those experiments. So, all right. Now, moving into measurements and units, what we're going to do is we're going to break this up into different segments here. So the first part is going to be dealing with measurements and the types of units. So first thing is that in chemistry we do a lot of measurements. So, and that's the most important thing, is to understand is how to make those measurements and the appropriate way of recording units and writing down those measurements that you make. So in the very end, you always can compare results to standards, but that's not always true, because sometimes you don't know what the standard is because it's something that you might be brand new to you. So, which in that case, you're making the standard at that point. So typical units that you come across are kilograms, meters, seconds, Kelvin, moles. All right, now those are measurements of mass, length, time, temperature, and the amount of substance. Now, yes, you're going to be using every one of these this semester. And so now this all ties back into SI units. SI units just stand for System of International Units. These are units that are used throughout the world, not just in America, but everywhere else. In fact, in America, we don't even use some of these units. We use weight in pounds and ounces. Our length is measured in inches, not meters. So we don't even use centimeters for that matter, but inches are the units that we like to use. Now seconds, yeah, we use seconds, hours. Temperature is Fahrenheit in America. So, but in the rest of the world, they use Celsius, and then Kelvin is the SI unit. Now, the SI units are the standard units that you use throughout the world. So anytime you make your measurements, so let's say you make a measurement in pounds. Well, if you want to report a journal, you need to convert your pounds into grams, and then grams gets converted into kilograms. That's what we're going to be focused on today, is we're going to be focusing on how to do those conversions and the conversion factors that we use to do that. All right. So this is just a basic FYI. It's just so that way you understand that here's why we use kilograms, meters, seconds, kelvins. It's not because we just use it because they tell us to use it. It's because that's what the world has decided that our standard units are going to be. So system of international units. So now in the metric system, we have our base unit, which is not on here. Our base unit is 10 to the 0 power, but we use these every day. And one of the things that you worry about, especially with your cell phones and your computers, is how much space you have on the hard drive. And so when we look at a typical hard drive now, what is it? 1 terabyte? Is that right? Do any of you have terabyte or 2 terabyte hard drives?
Yes.
It
Yeah,
actually depends on your hard drive space capacity and your computer's capacity to hold the thing
exactly.
in.
Now I'll tell you, this is kind of to show you how I'm not old, but I'm getting older. We all are getting older. When I was in your position, a 256 megabyte was like the top thing back then. Back then, you got a 256 megabyte hard drive, you had like the cream of the crop. Nowadays, if you have 256 megabyte hard drive, you wouldn't even be able to function with your computer or anything because it takes up things take up a lot more space now than they used to. So now gigabytes is something that you hear quite frequently, and gigabytes. So a 500 gigabyte hard drive, or in your case, if you have a phone, you might have a what's a typical space on a phone?
250, 256, something around that.
Yeah,
64 maybe.
yeah, that's about the most you're gonna get in a phone, which is a lot of space. So, but it's funny because gigabyte is 10 to the ninth, meaning that you have a billion bytes there. 10 to the ninth represents a billion. And so 10 to the sixth represents a million, and 10 to the third represents 1,000. So giga's obviously the biggest that's on this chart. And then you get down to centi, milli, micro. Those get to be really small. Now, if you look at micro, it's 10 to the negative 6. What does that mean? That means that you are a million times smaller than your base unit. Now, your base unit is just 1. Okay? So let's say you're talking about meters, for example. So if you have 1 meter, you're going to have a million micrometers that's there. So you have a million. So micro is real tiny. If you look at nanotechnology is getting to be pretty popular now, especially in the last 10 to 15 years. Nano is 10 to the negative 9. That's a billion times smaller than your base unit. So when we look at the meaning in this chart, it just really relates back to how big or how small the prefixes are. So now, when we look at problems, all right. Now this is a chart. So King Harry died drinking chocolate milk. This is a mnemonic that I've been using for a long time, and so this, how many have seen this before somewhere else?
Yeah, I've seen it before.
Has anybody never seen this before?
I've never seen this. I've seen something similar in biology class many years ago where they were doing like abbreviations for the different types of species, but I've never heard this one before.
All right. Well, what we're going to do here is we're going to talk about how to do simple conversions. And so let's say we have, give me a number.
73.
Okay. So let's say we have 73 meters. Okay. Now the question is, how many centimeters would be present in 73 meters? Now, your meters is right here with your base unit. So meters, so you have 4 base units. You have grams, liters, meters, and moles. So your meters is your base unit, and so centimeter. So king is kilo, This is hecta, which you will rarely use, but I put it there just for simplicity. This is deca. This is deci, centi, and then milli. Okay. So what we're going to do is we need to go from meters to centimeters. Now, the decimal place is right here. So all we're doing is moving the decimal place. In this particular example, centimeter is 2 places to the right. So we're going to move the decimal place 2 places to the right. Now, where you have these dips, you're going to put zeros in here. So what we end up having is 7,300 centimeters. So that's how many centimeters are in 73 meters. So all we're doing with this chart is just figuring out a way to move the decimal place left or right. All right. So now let's say that we have 73 milliliters. So we're going to use a different unit here. Okay. So let's say we have 73 milliliters. Now the question is how many liters is present with 73 milliliters? So now liter is your base unit. So milli is all the way to the right. In this case here, it's 3 places to the right. So what we want to do here is we're going to go back to the left because we're going from milli to liters. So what we're going to do is we're going to move the decimal place 3 places to the left. So we're going to go 1, 2, 3. So you have your decimal place there and you put your 0 in front. So this would be 0.073 liters. So that would be how many liters that you would have present. Now that's a small number because 70, remember milliliters is small. It's 1,000 times smaller. So if you only have 73 milliliters, you're not going to have enough to make a liter. So that's where some equalities come into play. So an equality would be, so for every liter, so for every 1 liter, you're going to have 1,000 milliliters. And when we look at it like this, okay, so the way we would go about calculating this using the equality. So that's what this is. This is a conversion factor. So we have 73 milliliters. We're going to multiply, because we're wanting to convert to liters here. For every liter, we're going to have 1,000 milliliters. So we're going to multiply by 1 and then divide by 1,000, because what we're going to do, our goal is to convert to liters. You want the milliliters to cancel out. So you end up with the same answer as we saw over here. So there's 2 ways of doing this. The first way is just moving the decimal place, or the second way is using the conversion factor to go from milliliters into liters. Any questions on that? Okay, so
Wait, um, just really quick, the gram, liter, meter, mole, the bar, is that signifying that that's the order? Gram, liter, meter, mole.
no, that's all that's telling you is that those 4 are going to be your base units. So like we said here, 1 liter is equal to 1,000 milliliters. You could say 1 gram is equal to 1,000 milligrams. You see how all I'm doing is changing the unit?
Okay, so this isn't going to be a mole to grams
No,
conversion.
not this here.
Okay,
No.
okay.
So you could have 1 mole is equal to 1,000 millimoles. That's all that's representing there. Now, what you're talking about is converting grams to moles using molar mass. We're not at that point yet, but we'll get there. So that's later down the road. So for now, we'll just keep it simple. All we're doing is converting using the decimal places here.
When
So,
will we get to the moles?
oh, that'll be probably another week or 2. We'll probably, I don't know if we'll get there next week because we have to get through atomic structure, and then we get into Avogadro's number, then we'll get into moles. So we've got a little bit of time before we get there.
Okay,
I'd
thank
say,
you.
okay. All right, so let's say we have 0.5 kilometers. How many meters would that be? So first of all, kilometer is what is on which side? It's on the left or right or in the middle?
The left.
It's to the left. It's the first one.
All right. And so how many places to the right would you go to get to a meter?
Three?
Three.
You got it. Yeah. So what we would do is we take decimal place and move it 1, 2, 3. So you would end up with 500 meters. Everybody understand that? All right.
Yes. Yeah.
Good. So that's about as simple as you can make it. That's what this chart's used for. It's basically a way to remember what direction to move the decimal place and how many places to move it. That's what that chart's used for. Now, as we move forward here, so volume, we'll see this in lab this week. Those that were in lab yesterday, you saw this, but those that are in the lab tomorrow and next week in Group B, you'll see this again. So liters, volume is measured, it's the space occupied by the substance, first of all. And so there are different units that you can use, but in the lab, we use milliliters and liters specifically. So looking at the graduated cylinder here, all right, and I'm going to draw this again just so we can see it's a little bit more pronounced. What we do when we look at a graduated cylinder is we measure at the bottom of the meniscus. So this curvature that you see inside of the graduated cylinder is called a meniscus, and you measure at the bottom of it. And so in this particular example, they have 1,000 milliliters as their measured value. So, so a milliliter is also, now this is just FYI, so 1 milliliter is also equal to 1 centimeter cubed. So if you ever come across that, you'll see it. Now, do any of y'all work in a hospital?
Yes, I do.
All right. Have you ever seen a nurse use the 2 letters CC? They'll say, "Go get me 1,000 cc's of this."
Yes, absolutely.
All right. So that is the same thing as a milliliter. So if they tell you to go get 1,000 cc's, they're saying they're getting 1,000 milliliters. Okay. So cc is the same thing as centimeter cubed, and that's where cc comes from, centimeter cubed. So centimeter cc's are milliliters, basically. So just FYI. Now, you might want to highlight that or write that down. What I just circled here. So the SI unit for volume is a cubic meter. So make sure that that's something that you write down somewhere so you don't forget that. Just FYI. Okay, so any questions on this? This is pretty easy slide. It's just basic information. I'm going to move on to the next slide here. So mass. So we have this piece of chocolate here. That piece of chocolate has a mass of 23.089 grams. The white plastic but underneath it here was zeroed out, so that was not part of the measurement. So what we're measuring is the mass of the chocolate. So mass is based off a standard, but mass is not weight. So when you see someone say that, let's say you had 25 grams, and you see someone say weight or specify that as weight, that's not right because grams is not weight. Grams is mass. So what the heck is weight? Weight is represented by pounds or ounces. And so pounds or ounces are actually determined by the gravitational force of Earth. So weight is determined by the gravitational pull. Mass is determined by a standard. Now we talked about earlier that the SI unit for mass is a kilogram. So that's already done in the past. But the main thing from this slide is making sure that you understand that mass is not weight. Mass is based off a standard. All right. Now we get to the fun part. So a lot of equalities here. Equalities are basically conversion factors. So that's all equalities are, conversion factors. So what I'm going to do is highlight the conversion factors that you need to know and the other ones you don't have to worry about. So I'm going to highlight that really fast here. So some of these you already know. Some of these you will want to go ahead and learn and make sure you remember them. All right, and let's see down here. Now this, so the metric system is just basically using that King Harry diet, drinking chocolate milk. I'm gonna write that right above it here. All right, so that's all that is. So the couple that you know these already. Those are circled there. So we know that there's 60 minutes an hour. We know there's 60 seconds in a minute. And then that would also equal to 3,600 seconds in 1 hour. So that's another one that you can write down. Because 60 times 60 is 3,600. So these are just one. So we're gonna use this table here in just a couple minutes. But any questions before I move on? All right. So earlier we had 73 meters. How many inches would that be? You're definitely gonna have to have your calculators for this. So if we have 73 meters, how many inches would that be? All right, so when I set this up, I'm going to have 73 meters times. Now, the conversion factor that I would want to use would be this one here. So since I want to convert to inches, I'm going to put inches on top. And I'm going to divide it by the meters. Why do you divide by meters? So the meters cancel out. You want the meters to cancel out so that way you end up with inches. So 73 times 39.37 gives me 2,874 inches. So that's a lot of inches. Now for a 5-foot person, a 5-foot person is 60 inches tall. So think about this, 2,874 inches. If a person's 5 feet tall, how many 5-foot tall persons could fit inside of that amount of inches? That's be a lot of people. So I would take 2,874 divided by 60. You could fit 48 people in that distance there. That's a lot of people in that distance. Now, so the way I figured that out is, again, I take the inches and I divide it by 60 inches because that's how many inches are in a 5-foot person. And that means that you have 48 people that could fit in. That's a long distance. So uh, that's how you do one conversion factor. Now, I want to talk about dimensional analysis before I go on because I think that it's a good time to sort of introduce what I call a T-chart. Okay, so a T-chart is basically a T. So the first thing that you have is it's a measured number. So it's given to you as a measured number. I'm gonna put measured above it here. Now this is called unit analysis or dimensional analysis. I'm gonna write this up here on top. So dimensional analysis. All it is just unit conversion, basically. So this is where the unit that is desired, and then this is where you have the canceling unit. So when we look at the example that we just did below with the 73 meters, so we have 73 meters, which is given to you. We were told that we're trying to find inches, so we know the conversion factor was for every meter, there's 39.37 inches. So since I want inches, I'm going to put the 39.37 inches on top, and I'm going to put meters on the bottom. So the meters are going to cancel out because that's your canceling unit. And so what do I do about this, the math part? So what you do is
Multiply.
you multiply. And so you multiply across, and then as you go top to bottom, that would be dividing. All right. So you still get the same answer. It's just a different way of setting it up. Okay. So the best thing to do is do more examples. So give me a number, anybody. Don't matter what number it is.
54.
Okay.
26.
All right, we're gonna go with 26. I heard that one. All right, so 26. All right, what unit did you want it to be? Give me a unit.
26 miles.
Okay, so let's say we walked 26 miles. How many meters would that be? All right, so we want to go. So looking at this, is there a conversion factor that converts miles into meters?
There is one that does miles into kilometers.
Let's do that one. Okay, so that I'm gonna erase a couple things here to get this slide looking a little bit better. All right, so you're talking about that one that I just circled, right?
Yeah.
Okay, all right, so yeah, we'll use that one. Okay, that's the first one. So what we'll do is we'll go ahead and convert our 26 miles into kilometers, okay? So so for every kilometer, there is 0.6214 miles, okay? So that converts that gets rid of our miles, and now we have kilometers. So we're trying to get meters, so now we see a conversion factor here where we can convert kilometers into meters, okay? So you can do this in a two-step problem. This is the first calculation, and this is going to be your second one. So there's 1,000 meters for every kilometer. So your kilometers are going to cancel out. So what you do is you take 26 miles, you're going to divide it by 0.6214, hit enter, and then you're going to multiply that number by 1,000, and that will give you your answer, which will be 41,841 meters. Does that make sense, everyone? Now remember, I can't see your chat box, so can
you go over that one more time?
Yes, please.
all right. So take your 26 miles. You're going to convert miles into kilometers first. So miles into kilometers, and then you then will convert kilometers into meters. Okay. So this is your first conversion factor, and this is your second conversion factor. What you want to try to do is you want to try to set yourself up a roadmap. Okay. So what this is here, that's your roadmap. So I know that what I got to do first is convert miles into kilometers. So what I did is I took 26 miles, excuse me, and I divided it by 0.6214 miles per kilometer. All right, does that make sense? That way your miles cancel out. That was the first thing. Does that make sense, everyone?
Yes, I think I just got lost because I didn't. If you could help by showing the work, I didn't. I wasn't doing the calculation. I was just writing what you wrote, and then when you came up with 41,841, I got a little lost.
All right. So you take your 26 miles and divide it by 0.6214 on your calculator, hit enter. You'll get a number, okay? You'll end up with 41.841 kilometers, right? Now, the second thing you'll do is now we have to convert kilometers into meters. So we know from the conversion factor that there's 1,000 meters per kilometer. So we multiply by 1,000 because you want your kilometers to cancel out. And so when you do that, you'll end up with the same answer that we have here. All right. So we'll do it. We can do one more here just for practice. So I'm gonna go ahead and erase what's down here so I can get that set up. So let's do this. Let's say we have, I don't know, who's the oldest person here? Not me. Don't include me. Anybody 25?
I'm 25.
You're
I'm
25?
36.
Okay. So my question for you is, how many seconds have you lived? That's the question. So we have a 25-year-old student. How many seconds have you lived in your life? So the first thing we have to do is we have to understand that we have to convert years into days. And then we convert days into hours, and then hours into seconds. So this is a multi-step problem. So the first thing we do is how many days are in a year? Not leap year, just a normal year. Anybody? I know y'all have to know this.
365.
Right. So there's 365 days in a year. All right. So your years are going to cancel out. So you'd multiply those two numbers together. Now, how many hours are in a day? Well, that's easy. There's 24 hours in a day. Now, the last thing here is we need to convert hours into seconds. Now, I gave you all a conversion factor earlier. I erased it, but it said there was 3,600 seconds in an hour. So your hours are going to cancel out. Your days are going to cancel out. So all you have to do in this one is multiply all this. So do 25 times 365 times 24 times 3,600. And wow, that's a big number. 7884000. What is that? 1, 2, 3. So you have lived 788,400,000 seconds in your life. Does that make you feel older now? You're not gonna answer.
Yeah.
Yeah. So you just think when you're 50 years older, just multiply that number by 2, and that's how many seconds you've lived. That means you have lived 1.6 billion seconds. It'll take you 50 years to get to a billion seconds, so unfortunately. It'll actually take a little less than that, but you get the point. So this is how we use the T chart. The dimensional analysis is what we call this technically. So is everyone on board here? Do y'all see the way you work a problem? So you always look at what's given and what's asking, and then you got to figure out what conversion factors to use to go from there to the answer that you're looking for. It's just unit conversions. Any questions on that?
No.
No.
All right. So we're going to do another one. This one's be a little bit more involved, but we're good. We've got to do it. I want to do it with you guys. So I wish I could just. All right. We're going to get it erased here in just a second. So what's the speed limit on the highway?
65.
Yeah, if it says 65, most people go 85. So we're going to go with that. All right. So 85 miles per hour. What I want to do is talk about, I want us to figure out how many meters per second that is. Okay. So that's our goal here. So how many meters per second would that be? Now, I'm going to do a simple one. I'm not going to do that one. I'm going to let y'all do that one. So let's say that we are going grand mal speed at 20 miles per hour. And I want us to convert that into, we'll do, let's say feet per second for just for fun. Then we'll do the other problem. So now there's two conversion factors, okay? So the first one is miles into feet, and then the second one will be hours into seconds, okay? So you got to be really careful when you're working these. So you only work with one unit at a time. Now, if we want to go from miles to feet, right here's the conversion factor. So for every mile, you have 5,280 feet. Done. Okay. The miles cancel out. So now we have our miles converted into feet. Don't need to do anything else. So the next one, now I want you to pay attention to the fact that the hours is in the denominator. So what we've been doing, we're going to have to flip it for this part. So for every hour, there are 3,600 seconds because you want your hours to cancel out. Does everyone understand that part right there? Is that you want your unit to cancel, so you have to make sure that the unit is going to cancel in the right way. If I were to have wrote it like this, 3,600 seconds per hour, yeah, our conversion factor is right, but what's going to happen is that the hours are on the bottom and they're not going to cancel each other out. So that we don't want that to happen. We want to cancel out. So what we do is we put our hours on top and your 3,600 seconds on the bottom. All right. So to do the math, you're going to do 20 times 5,280 divided by 3,600. All right. So that's how this would work. So you'd multiply here and then you would divide here. All right, so 20 times 5,280 and then divide by 3,600. That means I have 29.3 feet per second. That's still moving on pretty quickly if you think about it. So 5 foot tall person, I keep going back to a person because you can relate. Most people are around 5 feet tall. A 5 foot person, a car traveling at 20 miles per hour would run through, how many people would that be? 6 people. 6 5 foot people. So you would cover 6 people in a second. A second is that. That's extremely fast. Even though 20 is not that fast, it's still really fast. Now, think about 85 miles per hour. 85 miles per hour is going to travel how many meters per second? Now, a meter is, 39 inches, right? So it's 39.37 inches. So how many meters per second would that be? Now, in order for us to do this, so it's the same concept, okay? So the first thing that you're going to do is you're going to convert your miles into meters, okay? So to do this, what you have to do is you have to convert miles into kilometers and then kilometers into meters. The second part, we've done this just now, hours gets converted into seconds, okay? So let's start this problem here. I'm going to erase this stuff down here so I have a little bit of room here. All right, so to do this, we're going to have 85 miles per hour. I'm going to go ahead and convert miles into kilometers first. So there, for every kilometer, you have 0.6214 miles. And then I'm going to convert my kilometers into meters. I know that there's 1,000 meters for every kilometer. Okay, so that gets me into meters. I'm done with that part. Now the last part here is converting hours into seconds. So we talked about that just a minute ago. So for every hour, there are 3,600 seconds. So I'm just going to do, so going to do 85. So just make sure we understand. So 85 divided by 0.6214 times 1,000 divided by 3,600. So that's how you would type it in your calculator and hit enter. So I'm going to do that. All right, so what you end up with here is 37.8 meters per second. Now, we all understand well, I assume that you have seen a meter stick before. A meter stick is just a little bit longer than a yardstick. But when you're traveling a second, you're traveling 38 of those every second, going that fast. Now, if you've ever been in science hall, which I know some of you haven't, when you get to the science hall, when you get into the room, when you start at the very beginning of the room, if you were to walk all the way to the windows in the back, that's about 30 meters roughly. It's actually 25. So you would have to go through the room and about halfway into the pond on the other side of the building. You're traveling that distance every second. 85 miles per hour, you're carrying quite some velocity. And that's why people, when they crash at 85 miles per hour, the chance of survival is very little because of how fast they're going. Think about the momentum a 4,000-pound car would have if it were to start rolling at that speed. It would take it probably a good quarter mile before it would finally stop moving. So that's why when you're going real fast, you got to be very tentative to what's going on around you so you don't have any accidents. So, but that's the basic conversion factor.